Hi there. Thanks for joining us. This is Space Nuts. My name is Andrew Dunkley, your host, and it's good to have your company. I hope you're well. Coming up, we're going to talk dark energy again, but this time it's a very different story, and there's even potential for a Gnab Gib. Also, some exciting news from the Square Kilometer Array and baby exoplanets and their baby moons. We'll talk about all of that on this episode of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Yep, and it's very good to have Professor Fred Watson back in the chair, astronomer at large. Hello, Fred.
Hello, Andrew. Nice to see you again.
And you too. And making us look extra uglier is Heidi Campo, and Heidi will be our guest host while I take a few weeks off in a couple of episodes' time. But Heidi's going to be a part of these next couple of shows, learning the ropes, learning how to handle Fred. That's always difficult. Plenty of other things. Hi, Heidi. Welcome again.
Hi, guys. I'm sure Fred will not need too much handling.
Well,
She's
my
mad now. She's
my title has changed from astronomer at large to the astronomer on the loose. So, that tells its own story, really.
yeah. He's a wild boy. He sure is. Anyway, Heidi, jump in anytime if you've got a question or a thought or a comment, or you just want to leave. Whatever suits you. It's all good. Let's start by a story without notice, which we gave notice of last week, and that was the return to Earth of Butch Wilmore and Suni Williams. They are back on Earth after their 10-day mission. Yes. Which ended up being 286 days, I'm told. That's quite incredible. One of the things that fascinated me was as soon as they splashed down, a pod of dolphins circled the spacecraft.
Lovely.
I thought that was really cute. But they're back on Earth. I did a bit more reading on what went wrong. The poor old Starliner, it showed some booster problems, but then there was another problem with leaks, and they decided to not send them back on it just in case, and it came back to ground safely, of course. And then it was all about how do we get them back to Earth, and remember, Fred, we were talking about the lack of compatibility of their spacesuits.
Yeah.
I mean, all these problems just kept piling up, and it turned their mission into something much, much bigger. I reckon they'll make a movie. They will make a movie about this.
I think you're probably right. Fortunately, we know it has a happy ending, so that's
yes. Well, I think there's enough in the story to warrant a movie, because there were things that happened on the space station that involved them, like record-breaking spacewalks, and I think Suni became the commander of the ISS there for a while, and of course then early this year, the US president and Elon Musk got involved. I mean, it just it's got movie written all over it, I reckon. I don't know, Heidi. I mean, our perspective might be different. You're in Houston. You're sort of at the coalface.
Certainly am in Houston. Well, I think as far as the American opinion versus the Houston opinion is a little bit different. It seems like, and I can't speak for all Americans, but it seems like a lot of Americans are mixed bag of nuts, and some people are really happy that the astronauts are finally back. I'm sure the astronauts are happy that they're back. Yeah. And then some people are, hailing the rescue mission, but then, here in Houston, everyone's saying, hey, this is what they train for. This is what they plan for. And there is not a single astronaut that's going to be upset about bonus time in space. Yes. And this was not, it seems like an emergency situation, because we watch movies like Gravity where everything goes wrong and we're just thinking complete chaos. But for them, this is what they do. They're professionals. And while it may seem like a big chunk of time. This just gave the astronauts more time to do what they love to do. And that's, I think it's a beautiful thing. And it wasn't kind of the way that some people are seeing it. You know, the astronauts are fine, and this was planned for them to come back at this time.
Yeah. I suppose what happens now is they've got to get their Earth bodies back. Because being in space for a long period of time, as Fred and I have discussed, can have a big impact on your skeletal and muscular systems. And getting back on Earth is it's a task.
Yes, and that's actually the research that I'm specializing in right now, is the countermeasures in human spaceflight research and getting them back to Earth gravity ability.
Yeah. Oh, looks like we picked the right person to take over from me, Fred. So I won't be coming back. But it's good news. Butch and Suni back on Earth and celebrating Christmas a couple of months late. Now, we are going to look at this story that's popped up. I spotted this the other day, Fred, about dark energy. And I read the whole story. My brain hurt. I took a couple of ibuprofen and settled down. And then I thought about it. And I simplified it by saying dark energy may not be doing what we first thought. And I also saw a reference to the possible return to the collapse of our universe sometime in the long, long distant future, we hope. So this is a really interesting story to unpack.
It is indeed. And it's a story that I guess it's still only a quasi story, in that the evidence that is being presented for dark energy weakening over time is still tentative, if I can put it that way. And admittedly so. The authors of this study are not saying, yes, we've firmly discovered that dark energy is weakening. They're presenting it in those terms, a tentative discovery. So what are we talking about here? Back in 1998, we thought the universe was well behaved and gravity of everything in it would pull it together, and one day it would collapse on itself in what some call the Big Crunch, but you and I know the correct term is the Gnib Gab, which is the Big Bang backwards, courtesy of Brian Schmidt. And that was apparently blown out of the water by Brian Schmidt and Saul Perlmutter and a few other scientists who had two separate projects looking at the expansion of the universe in detail. And suddenly we realized that the expansion of the universe is accelerating. In other words, it's getting bigger, faster. And so that led to the concept of dark energy as being the sort of propulsive source for this. An energy, of space itself, some essence of space that as space gets bigger, this energy gets bigger as well. So the thing is, it's a system that is self-propelling, in the sense that it, the bigger the volume of space, more energy you've got. And the simplest assumption that you can make about that is that it can be represented in the equations of the expansion of the universe by something we call the cosmological constant, which is it's a crap name, really, to tell you what it's about. But that was effectively a term in an equation that was inserted by a gentleman by the name of Albert Einstein when he realized that his equations of relativity wanted to make the universe expand or contract. And at the time, back in 1915, he thought it wasn't doing any of those things. So he put this cosmological constant in to stop the expansion in the theoretical basis. Then, of course, in 1929, Edwin Hubble discovered that the universe is expanding, and Einstein later called it his greatest blunder. But that is not what we have seen it since 1998, because cosmology has really adopted the cosmological constant as being the most likely interpretation of the acceleration of the universe and of what dark energy is doing. It's saying it's proportional to the size of the universe. So the more universe you've got, the more dark energy you've got. You can, however, test that. And I remember giving talks on this probably 15 years ago, where people were talking about testing it by looking at the large-scale geometry of the universe, which is traced by galaxies and these strings of galaxies and filaments of galaxies and membranes of galaxies in the wider universe, this sort of honeycomb structure that we know the galaxies occupy. And so if you can map that accurately, then you can get insights into actually not just dark energy, but dark matter, things like the neutrino content of the universe. This all drops out of the way the geometry has developed in the history, the 13.8 billion year history of the universe. So back in Australia in the early 2000s, a survey of the positions of galaxies was started, what's called the 2DF Galaxy Survey, 2DF being the 2-degree field system on the Anglo-Australian telescope. That mapped galaxies out to about 2.5 billion light years away. Fast forward to 2025, and we now have surveys that are mapping galaxies back to 11 billion light years away. And that's where the cracks are starting to show up in the cosmological constant, because the evidence coming from something called the Dark Energy Survey Instrument, which is on a telescope very similar to our Anglo-Australian telescope at Kitt Peak in Arizona, the Male telescope, that is starting to show, because they've basically evaluated the geometry of the universe over these much greater look-back times. It looks as though dark energy was stronger 11 billion years ago than it is now. And that's, as I said, it's not a conclusive deal yet, but the evidence is strong enough that people are really getting excited about it, because we don't understand it.
Yeah.
It's not predicted by relativity.
And that's what makes it so complicated and hard to get through your head. But the scenarios that the popular press have jumped on is, look, if the universe continues to expand at an ever-increasing rate, which is the current thinking, it will ultimately rip. But if this new study is right and things are slowing down, it might just collapse back in on itself. If none of those things happen and the universe just sort of hangs like on a street corner, it will just eventually burn out and become a cold, dark place. So they're the three potential fates, aren't they?
Yes, that's right. Well, as we understand it, the thing about this is, if it shows holes in relativity, and that's the exciting bit. People have been looking for cracks in the theory of relativity basically for 100 years, because relativity is such a good theory. It's very hard to find anything in it that is not replicated in the real universe. The theory predicts the real universe very, very accurately indeed. But there are some things that we think are anomalous. There's this tension between quantum theory and relativity theory. There's dark energy itself, which we don't really understand. There's dark matter, which we don't really understand either. And these are all things that maybe need new physical theories to understand. And so when you start finding cracks in relativity, maybe that is going to give us a window into these new ideas that might let us understand what dark matter is, what dark energy is, how quantum physics interacts with relativity, how the two come together. And you never know, Andrew, some of that might actually be useful. It might be stuff that we could make use of on the human scale, in a similar way to the fact that relativity lets us have a GPS system in one of these.
Yeah, absolutely. And Einstein himself always believed that his general theory of general relativity was flawed. We just haven't found the cracks yet.
He did. He went through his life looking for the evidence of exactly as you've said, flaws in general relativity, new physics that would, in his case, principally unify quantum mechanics and general relativity. He didn't know about dark matter and dark energy. He died in 1955, well before. Actually, we knew about dark matter then, but nobody talked about it because it was too hard to understand. But anyway, he didn't know about those things.
Yeah, it could, but as you said, this is only a theory that's in its infancy. They've got a lot more work to do to figure out whether or not they're right, and we're heading for a big crunch or whatever you want to call it, a Gnab cube. Yes. All right. If you'd like to read that story, it's all over the web, but there's a great article at the Conversation website. This is Space Nuts. Andrew Dunkley here, Heidi Campo there, and Fred somewhere else.
3, 2, 1.
Space Nuts.
Okay. Our next story is getting a bit closer to home, and this is one we've talked about many times, the Square Kilometer Array, that wonderful device that they're building out in the Never Never of Western Australia. And even though it's not finished yet, and they're going to probably not complete it until 2030, the exciting news is that they've taken their first image, and it was a selfie. No, it wasn't.
Yeah, this is a great story. It's the Department of Industry, Science and Resources, who until recently was my employer, is basically the federal agency that looks after the Square Kilometer Array. So this is a story very close to my heart. And I'd love to congratulate all my colleagues in that department who've been working on this, and of course the people in the Square Kilometer Array Observatory and the CSIRO, the Commonwealth Science Industrial Research Organisation, Australia's National Science Agency, all of those people too, because this is a great step forward. I can't remember whether I've mentioned this to you before, Andrew, but I played a small part in this because back in, I think it was 2018, I was part of a small group that fronted up to a parliamentary committee, something called JSCOT, the Joint Standing Committee on Treaties.
Yes.
And it was to persuade the government of Australia that signing a treaty with the International Square Kilometer Array was a good thing. And they asked the astronomer at large what his view was, and I told them they had my personal guarantee that this telescope will produce Nobel Prizes.
That's right, you did too.
So I've got a vested interest in this thing working,
Yeah.
even though it does have a 50-year lifetime, and I don't, probably from now. You never know, could be. But the thing that really tickled me was that it went into Hansard, the parliamentary record. So that is my contribution, which is vanishingly small compared with what everybody else has done. So where is it? The telescope is at the CSIRO Murchison Radio Astronomy Observatory in Yarimana, Ilgari Bundara. And that Wadjuri name is something that translates as me sharing sky and stars. The Wadjuri Yamatji people are the traditional owners of the land on which the telescope is, and so the site has an Aboriginal name, a Wadjuri name, which is lovely. It is something like 350 kilometres northeast of Geraldton, which is on the northern coast of Western Australia. It's in a region that is perhaps one of the most radio quiet regions on the land surface of the world, because there's no external interference from terrestrial sources. And so that's why it's there. It's because it's such a radio quiet region. I have had quite a lot to do with trying to keep it that way, though, because, of course, one of the things that interferes with the radio quietness are satellite megaconstellations. And that's one of the things that has occupied my time over the last few years to be concerned about them and work with collaborators on how we can mitigate that risk. Anyway, that's a different story. The bottom line is this telescope is the low frequency arm of the Square Kilometer Array Observatory. The mid-frequency arm is in South Africa, which will have 197 dishes, very like the Parkes dish, that we're all familiar with here in Australia, a standard radio dish. However, the low frequency telescope in Western Australia consists of a whole lot of metal Christmas trees.
Yeah.
About 2 meters high. There are going to be 131,072 of these Christmas trees. But there has been a start made, and we now have working 1,024 of them. And that 1,000 or so of the antennas is what has generated this first image that was released last week. And it is a major triumph. Just to give one little insight into the complexity of this telescope for both you and Heidi, when it's finished, its data capacity will be more than today's internet. So
Wow.
it's a lot of data. It's an incredibly complex system. When the telescope was planned, there weren't any computers in the world that were fast enough to actually, make it work. And we've moved along from that, as we can see, because the first 1,000 antennas are actually doing their thing. So an extraordinary, instrument with, I think, a very bright future, a radio bright future, and the first big step in putting it on the map as an astronomical instrument. What did it look at?
Yes.
It's a 25.
That's what
I read your mind. I read your mind there.
You did.
Yeah. 25 square degrees of the sky in the southern constellation of Sculptor, and basically looked at radio galaxies in that 25 square degrees. It detected, I think, 84 of them. These are all galaxies that have been known from other explorations. And of course, the telescope is nowhere near its final sensitivity yet. It's going to be hundreds of times more sensitive when it gets the full array. But that's a great start, and everybody's delighted with the image that was released, especially the scientists working at the Square Kilometer Array. When the thing is finished, that same bit of sky, it will reveal something like 600,000 galaxies rather than 84.
Yeah.
And some of those galaxies will probably be the first galaxies forming in the universe, because you'll be looking back so far in time. We'll see the end of the Dark Ages, when nothing was shining in the first few 100 million years of the universe. So it's going to look back a long way.
It's still hard to get your head around the fact that we'll be able to see what was there before. I know we're moving forward in time constantly, but there's just still all this evidence and information and historical data, if you like, that gives us that kind of insight. I think that's amazing. I tried to explain it to my grandson, and he just went back to Pokemon. But it was
just tell him that he's seeing Pokemon as it was a billionth of a second ago.
Well, I don't think he'd get that either. But it is quite extraordinary, and this thing and the one in South Africa that I think it's called Meerkat.
Meerkat's the initial version.
Yep.
Meerkat, it'll be a kind of mega meerkat.
Yes. It promises to open big doors, just like the James Webb Space Telescope and the Vera Rubin Telescope and all those new things coming online. These next 20, 30 years are going to be extremely exciting.
That's absolutely right.
Yeah.
Just one other thing, the SKA will probe the whole history of the universe, basically, including today's universe. So my radio astronomy colleagues tell me that the sensitivity of the final telescope will be enough that it will be able to detect an airport radar at 50 light years away.
How awesome.
So if there are people leaking radio waves into space from the stars of other planets within 50 light years, we're going to know about it.
Wow. And they probably set up their own Square Kilometer Array. And
I have, yeah.
they'll find us too, maybe. I don't know.
Are there any concerns with more and more satellites getting launched and radio waves in the atmosphere of anything disrupting these highly sensitive and advanced tools?
Absolutely right, Heidi. They are, and those concerns are what I mentioned a minute ago. It's there's a lot of activity in the astronomical world in how you can mitigate the effect of these satellite constellations. it's possible. So just sidestepping to this for a minute. At the moment, there are just over 11,000 operational satellites in orbit, of which 7,000 are Starlink in low Earth orbit. Starlink's got a mandate to launch up to 42,000. There are many, many more. So it's likely that by the end of the decade, there'll be 100,000 spacecraft in orbit with 50,000 above the horizon at any one time. And they're all beaming down radio signals. Now, Starlink, SpaceX actually is one of the good players in this because they turn their satellites off when they're over radio astronomy observatories. They switch off the beams. However, there are other issues because the electronics of the spacecraft themselves are quite noisy at the level that these sensitive radio telescopes can detect. So there is a huge amount of work going on as to how you can rectify this. You can't get rid of them. They're a fact of life. There are going to be more of them. They actually do good stuff because they provide high-speed internet, on a global scale. But it's changing astronomy, both visible light astronomy and radio astronomy. Astronomers are now having to deal with this interference from satellites. So a lot of work going on that, and I talk about it incessantly, so I'll shut up.
Yes.
Yeah. I've heard even astrophotographers are having harder time getting long exposure shots.
That's correct.
Yeah.
Yes.
Yeah. And of course, Heidi, you probably have already figured out what I've figured out, that this first image of the SKA is actually just the satellite array of Starlink, and it's not actually galaxies at all. But yeah, oh well, that's the way it goes. No, I'm kidding. Sorry, Elon.
As a lot of people will be very upset about that thought. Yeah. But fortunately, none of them listen to this. So
yeah, that's right. Yeah. And once they get to know me, they'll realise I'm just full of it anyway. But of course, the most exciting thing about all of this, Fred, is that I know where I'm going for Christmas in 2030 because, I can't fit 131,000 Christmas trees at my place. So that's really exciting. That's going to be fun. Yeah. If you'd like to read up on that story, best place to go would be the Square Kilometer Array website, the SKA Observatory website. Easy to find, skao.int. We'll get you there.
0G, and I feel fine.
Space nuts.
Now, one final story, Fred. This one, everybody loves babies. We've finally found baby moons that are forming around baby planets.
Which is a neat segue to let you know how our baby is doing. My new granddaughter, Aggie, she's now almost a month old. She's 3 weeks old. She's doing very well, thank you. Thank you for asking.
Congratulations.
Oh, thank you, Heidi. What were we talking about again? Yes, we were talking about baby planets. And this is some work that has come from actually a telescope in the Southern Hemisphere. What's happened here? My crib sheet's disappeared. There we are.
Fred can lose pieces of paper that aren't even real.
Yes, so just done it. This is on the work coming from the 6.5 meter, or one of the two 6.5 meter Magellan telescopes, which are at Las Campanas Observatory in Chile, a place which I visited. A very nice dark site for astronomy. But these scientists, who are principally from the University of Arizona, up there in Tucson, they have been observing with something called an extreme adaptive optics system. So, we're familiar with ground-based telescopes having to look through the atmosphere, and that's why we put telescopes in space, because the atmosphere is not there. So down here on the Earth, we've always got the turbulence in the atmosphere to deal with. But this technology of adaptive optics is now actually making imagery that is even finer detailed than space imagery is. And so we are not really surprised when we get results like these from the Magellan Adaptive Optics Extreme Instrument, MAG-AO-X to give it its full name, which shows a protoplanetary disk around a star which has the glamorous name of PDS-70. PDS-70 is a star which is young, something like 5 million years old. That is very young indeed. It's our sun is 4.5 billion years old, so this is 1,000 times younger. But it has a protoplanetary disk around it, the disk of dust and gaseous debris that we recognize as being the way planets are formed. And within this disk, some planets have actually been identified. They have been imaged. And that's quite unusual. As you and I know, Andrew, the normal way that we investigate the planets of other stars is by the effect of the planet on the star itself, which we can then observe. But this is a direct image of two planets, which are PDS-70b and PDS-70c, and they are sort of going to be, they're still growing, they're still accreting material. They're probably going to be much bigger than Jupiter, but there is evidence from the imagery that the planets themselves have a protoplanetary disk around them. In other words, the planets also have a ring of stuff around them, which is where we think moons form. We believe our own moon formed from a ring of debris caused by an impact of an object we call Theia, the size of Mars back in the day. So a really nice piece of work suggesting that moons of exoplanets are a reality. We can expect to find more of them as the technology improves. And the big game changer, of course, will be the European Southern Observatory's extremely large telescope when it comes on stream in 2028, which will be able to form direct images of these things.
Yeah. How far away is this object?
It's actually quite a way. So I think 370 light years comes to mind. I think that is its distance. And that's, that's certainly not on our doorstep. It's in the sun's neighborhood in space, but it's not among the nearest stars.
Yeah, but to be able to analyze something so far away and find data that suggests, look, we've got protoplanets and proto-moons happening here, that's pretty darn amazing.
I think so too.
Yeah.
So congratulations to colleagues at the University of Arizona.
Yep, good for them. Yep,
Got some very good friends there, actually.
You have friends everywhere, Fred.
Well, in astronomy, it's such a small world, you do.
Might have a friend on Mars soon. You never know. Nope.
Somebody called Elon, do you mean?
Oh, dear. That story available at space.com if you want to have a look at the images. They're artistic representations, but it gives you a pretty good idea of what they've found. And that brings us to the end. Anything to add, Heidi, to finish off? You know, this has been a learning process for you. I'm sure you're going, what the heck have I got myself into?
No, I'm thinking about so many things, and I have questions lining up probably for future episodes.
Good. That's what we want. Excellent. All right. Well, thanks for sitting in, and we will catch you on the next episode, because that's a completely different kettle of fish, our fish being listeners. And Fred, thank you to you as always. I don't know what that meant either.
You're welcome, Andrew. You're very welcome, as always.
Oh, gosh. Time to go. And thanks to Hugh in the studio, who didn't turn up today because he knew what he was getting himself into, and he didn't warn Heidi about it at all. And from me, Andrew Dunkley, thanks for your company. See you on the next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.